focus this afternoon will be on Hooke's law. It's a popular topic in physics. Hooke's law of elasticity. What we shall be doing, we will be applying it to attempting problems involving practicals. It has to do with the use of a string. So we use it to simply calculate either the force constant or the extension. So it's vital for you to understand what Hooke's law is talking about. In simple terms, before I define Hooke's law, all you need to know, it talks about the force directly proportional to the extension. The E is the extension. Many times you write it as force directly proportional to change in L. And the change in L or E is known as the extension. So that is just a mathematical expression of Hooke's law. So we shall be applying it to a practical exercise and then we'll see how it goes. So now we have two parts of the experiment we are going to be looking at. You see the end. Number one says to determine the force constant of a spring statically, while the other one is dynamically. Now the first one, to determine the force constant. The force constant is from Hooke's law, like I said, provided, stating the number, it says provided the elastic limit is not exceeded. The extension of the wire is directly proportional to the load or applied force. The extension of the wire, that's E, is directly proportional to the load or applied force. The load or the applied force is this F. So mathematically, it simply means F is directly proportional to E. Now I'm changing this variation sign to an equality sign. Now it simply means F is equal to KE, or F is equal to K change in L. Remember what I said, this E is the extension, this change in L is still the extension. So many times you can see it like this or like this. Okay, so this is just a simple illustration of what Hooke's law is talking about. Many times what you will be plotting is the force against the extension. Plot the force against the extension, you can find the K. The K is a mathematical constant. So this force is just like the Y equal to mx, equation of a straight line. So y-axis, x-axis, x-axis, k-axis, gradient, that's the slope. So let's use it to apply for the first case now. Simply determine the force constant of a spring statically. Statically simply means the spring, the masses, they are simply on a particular spot, they are not moving. So I could have series of masses placed like this, it's static, it's not moving. Dynamically, in this case, I'm moving it. So this experiment is of two types. So one is static, one is dynamic. So for the static, you can see the learning outcomes. They expect you to be able to state Hooke's law, which we have said, we discussed, and enumerate the factors affecting the spring constant. There are so many factors that I was going to here. You can see some of the factors here. Material of the spring and the thickness, that's the diameter of the wire. It has a lot to do with, to tell concerning the factors that affects the spring constant. Now, so the third one says set up an experiment to determine the spring constant. The spring constant is which one?
Constant.
The spring constant is which one?
It is the E.
It's the K.
Okay.
K. This is the force or load. This K is the spring constant.
Okay, spring constant.
Constant K. This E is the extension. Don't mix it up, otherwise you get confused. So
E is the extension,
yes,
K is the spring constant,
yes.
and then F is the force.
First, many times you see
Or
that's
load.
load. So you want to set up an experiment to determine the spring constant using static number one and dynamic number two. So you use two methods to find the spring constant. You understand? Now the apparatus you'll be working with, we have the spring holder, the spring itself, vertical ruler, set of masses, and stopwatch. Now let's go through the theory. The first one says determination of the spring of the first constant of the spring. The first constant of the spring is still the spring constant. Now, if a mass n is hung from the lower end of the vertical spring, it causes the elongation of the spring, that's true, by an amount delta change in L. This change in L is the E, remember, I said so. Yes, if you don't see it like this, you see it written as E. Now, I go again. If a mass is hung from the lower end of a vertical spring, it causes the elongation of the spring by an amount change in L. This sign is change in or delta. That depends on the value of a mass and the properties of the spring, the material, its length, and its cross-sectional area. These are what affects the spring constant. Now, Hooke's law states that the applied force is proportional to the extension produced. That's what we just explained. They are stating Hooke's law. Now, F is equal to K. See what we did here. Just know that formula. Where K is what? We call it spring constant, we call it force constant. But also take note, F is equal to mg. You should be familiar with this formula. Force is mass times gravity. That's gravitational force. Gravitational pull of the earth. That means mg. This g simply is the acceleration due to gravity. Next one, we were taught that in physics. So F is equal to mg. Now let's get this one. Therefore, if we plot the relation between F and the extension, we get a straight line that passes through the origin. So your graph will pass through here, which will help you calculate the slope. So that slope K is in Newton per meter. That's the first experiment we're going to do. Now, the second experiment, all these are to help you. I don't want to go into details now. The second experiment, what they expect you to do is, you are going to, this is an equation of a straight line. You are going to use it to calculate y equals mx plus c. You are going to use it to calculate the slope and the intercept. The intercept is where this line meets this vertical axis. This point here. We will get to that. Now let's look at the procedure. For the first case. At the startup, the apparatus will be set to be shown in the figure. The masses are stacked on the table while the spring is hung from the vertical stand. See, this is the record stand. See the spring here. This is where you place the mass. This thing is here, this mountain, it's spring. So if you put mass here, it will come down small because it's spring. Okay, I don't know if you understand. See the masses here. You pick one and drag it on top here. Usually for 30, 40 gram or whatever. So if you pick one here and drag it here, if you put it here, this spring will come down small. That's to tell you that the mass have weight. To come down. Now, before then, you measure this original length. This measurement now you read it on the ruler here.
Okay.
If for example it's 5, by the time you pick the mass and put on top, it will have gone down to somewhere here. That's length that change now is the extension.
Okay.
It's not the original length. This is the original length. When I put this thing now, it will bring it down small. From that original length now, there is a change. So that change now is E or delta L. You will now take note of that reading. So that is what this one is talking about. Now, the red horizontal line is the indicator you will use in the first pass to find the extension code. Now, number 2, click once on the masses. At the masses start, you click once here, then take it there. This will cause one piece of them to be hung from the hanger. To unload the spring, click on the hung masses. And when you want to remove it now, you click on it. Now you will be zoomed in on the scale to find the position of the indicator. Click the record button to record the mass value and the corresponding extension. All these ones now they are for static. That extension is delta. Now you're going to repeat the previous step for all the existing masses. So if you are starting with 30, after 30 you do for 40, you do for 50, depending on the number that is given. Now when you finish recording at all the data for the existing mass, the data will download automatically just by the first case. So that's what is involved here. Now look at these are the values you say you should use.
I don't think so long.
The downloaded Excel sheet will contain the results you have recorded in column A and B. Now look at the A. For 50, there's an extension. For 100, there's an extension. For 150, the mass as it gets larger, it will be dragging the spring down. If I put this phone on top of the spring, you can compare it when I put 3 phones. 3 phones will drag it down. So expect the extension to be increasing as the mass increases. That's what we mean by direct proportional. If it's reducing, the other one will be reducing. If it's increasing, the other one will be increasing. So at the end of the day, for the masses now, you will get this extension. To get this to you, not fill every other column. This column C now, you have to convert the mass to kilogram. The mass there is in grams. Convert the mass from grams into kilogram. So 50 grams in kilogram now is divided by 1000. That will give you this one. Then you convert the extension from cm to meter. That's for this one. Look at it. In column D, convert the extension in column B from centimeter into meter. All you do is to divide by 100.
I divide whatever is here by 100.
2.45 divided by 100.
Okay.
4.9 divided by 100. This divided by 100. Do this. So all of them here divided by 100. You get this. Understand? Then in column E now, you calculate the applied force. Okay. The formula you're using now is mass times gravity. This one. The mass times gravity is the mass in kilogram now. The mass in kilogram from column C times 9.81. That 9.81 is a constant. Take G, they give you G as 9.81 meter per second squared. It's called acceleration due to gravity. It's a constant.